Right, so now that we have some information about trapezoids and tessellations, let's talk about some examples. We have been given some information. We have isosceles trapezoid TVZY, and the question is we're trying to find the measure of angle T. So a couple of things I want to point out. Isosceles, that term lets us make some decisions on what we have in front of us. Here is our isosceles trapezoid. They've already kind of given away one of the important pieces. We've got two sides that are congruent because in our isosceles trapezoid, the legs are always congruent. Those are the sides that are not parallel. You can see here we have our two parallel sides. We've been told that the value of angle I is 60. We know that in any isosceles trapezoid, the base angles are congruent. We have a set of base angles here, and we also have a set of base angles here. So we've got that information just as part of the gig. You know, this is, we can immediately make that decision. Because we know this to be 60, and we have congruency between these two angles, I can immediately change or make a note here that this angle measures 60 degrees. The question was find the measure of angle T, and we didn't have to do anything. We literally just used the property of isosceles triangles, which tells us that our base angles are congruent, and it got us what we were looking for. Now, they didn't ask us about Y and Z, but let's just do a quick look. Let's take a look at our parallel lines. Remember, these two lines are parallel, and back in the days of just learning about parallel lines, we see a scenario that kind of looks like this. And when we do that, our parallel lines cut by this transversal, we have the value of this angle is 60. We know they're not congruent, but look at them. They're living on the same side inside, or in what we call this consecutive interior location of two parallel lines. So if I was to try to find the measure of angle Y, I would use the supplemental relationship between those two angles, or the supplementary relationship. And all I need to do is subtract 60 from 180 to come up with the value of angle Y. All right, so let's go to the back. A couple more examples to talk through. We have another isosceles trapezoid they've given us, so let's just kind of highlight that information. And the name of him is PMNO. All right, so he's over here. We're looking for some angle measures. Now, they have done a couple of things inside this isosceles trapezoid. They've given us the value of one of the base angles down here at, or up here rather, at 48 degrees. They've also shown where they have dropped what we call an altitude in between these two lines. Let's make a couple of notes on our trapezoid. We've got our two parallel lines living above and below. Of course, it could be flipped on its side, but in this case, they are above and below. And we've also been told, again, this is an isosceles trapezoid, so just for giggles, just to make our marks, because we can legally do this once they give us that information, I'm going to show these two sides as congruent. I just mentioned the fact that we have a base angle provided to us, and he's 48 degrees. We know what the base angles in any isosceles trapezoid are congruent. Okay. Now this line, again, is in our way, but it's going to give us some helpful information soon enough. We know this to be 90, and since this side of the line is 90, this side will also be 90. That'll be helpful soon enough. We also have these other two base angles down here at the bottom. Now I might choose to draw this separately just to kind of help myself keep all these properties straight. Just to kind of go back to what we were doing, right? We've got our congruency on our sides. We've got base angles up top congruent. And then we also have these two specific angles congruent. Oops, that's not a very pretty congruency mark, but hopefully you get the picture. So these two guys are congruent as well. Just to show that in our picture above, I would show it here and here. Now keep in mind I'm crossing over that angle here. Don't let this line scare you. He's just in the way. But nonetheless, we do have congruency here and here. So that's kind of what I can mark at this point. I can put some other values in there, but let's just find out what they're looking for first. So the question is, we're looking for the measure of angle PMN. And remember, when we're trying to find an angle value based on letters, we need to follow a path. We're going to go from P to M to N. So it was this particular, in fact, I'll just draw the picture, draw the line. So from P to M to N, yikes. Okay, so we're looking for the value of this guy. Fortunately, we have already made some markings for ourselves just to kind of make our life a little better. Let me get rid of some of that trash now. And let's remark these as well. So again, this was a parallel mark, and I had a congruency mark here and here. So if I'm looking for this angle, and I know these two guys are congruent based on our properties of isosceles trapezoid, this is nothing more than 48 degrees. Okay, then I'm moving on to angle PON. So I'm going from P to O to N, which is this guy that I've already marked with two green marks. Let me just kind of show it again. All right, so we're going to go back to kind of the way we looked at this on that last example. Kind of look at our parallel lines like we learned about it back in the day. I cut my transversal through there. So I have a set of what we call supplementary angles, right? Same side interior, same side of the crosswalk, inside the road, whatever you want to remember how to do that. So the value of this angle is going to be 180 degrees minus 48 degrees. And when I do the math, I will get that this is worth 132 degrees. All right, so if at any time you need to pause the video because I'm swinging through this, please do so. I want to make sure everybody gets the information. I'm going to erase all these marks for myself. Now you guys might have a bunch of stuff going on yours, but that's okay because we're going to do some redrawing in a minute. We know this is 48. We decided above that this angle is also 48. We have the value of this angle is 132. And we know that this entire angle from here to here is also 132. But I'm going to hold off on that. By the way, that's an 8. That doesn't look very pretty. I'm going to hold off on that. The next one I need to find is angle MNQ, which is this angle down here where N is my vertex. And I'm doing this on purpose. I'm going to just keep going with my picture. This is the angle we're looking for at this point. Okay, so we need to use some of the tools that we've learned in the first semester to come up with that. Go ahead and pause the video, come up with the value of x based on the information given, and then see if you got the right, see if you got the same thing as me. All right, and you should have gotten that the measure of angle MNQ, this guy right here, is worth 42 degrees. We used our triangle sum theorem to come up with that. All right, going on to tessellations, and we discussed the use of tessellations, the fact that tessellations always occur in 360 degrees, or rather the sum of a tessellation, some of the angles in a tessellation is 360 degrees. So let's just reiterate that. Sum of the angles in a tessellation is always equal to 360 degrees. And that's hugely important with what we're about to do in terms of these examples. We've got all the information we need already based on what we've learned about angles of polygons to really rock through this. I want to make sure you guys get the fact that this isn't overwhelmingly challenging. You just kind of got to get an understanding of what you have to find first to come up with what we're looking for. This says a design for a special pen. Included a regular nonagon and an equilateral triangle as shown. What is the measure of angle DCB? Well, here's angle DCB. It's this guy out here. It's essentially, we're looking for the value of this angle. Now, we mentioned the fact that a tessellation, the sum of the angles in any tessellation is always 360 degrees. And the easiest way to kind of see how this rocks is to draw us a circle. And we're going to draw it all the way around this sort of center point. Okay. Now, we haven't gotten into circles deeply, but we do know that the sum of the angles in any tessellation is 360 degrees. We just saw that. And frankly, that is really the root scenario of any tessellation. You're basically going from one point all the way around to the other. And when you sum up the angles inside there, you'll always get 360 degrees. So our goal in order to find x is to come up with a value for this angle here, and also to come up with a value for this angle here. Now I'm going to use just dots just because I don't have a whole lot of room inside my happy circle that I've drawn. But let's do this in 2 steps. Well, it's really 3 steps. We'll start with step 1. We need to determine the value of this angle. Now we've been told the important information above is this is an equilateral triangle. If he's equilateral, then not only are all his sides congruent, but his angles are as well. So in order to determine, I'm looking for the interior angle measure, right? And this is just going back to using what we already know about angles of polygons. The interior angle measure of a regular polygon means you're going to take the sum of all the angles and divide it by the number of sides. And we know, because this is a triangle by heart, that there's 180 degrees in a triangle. There are 3 sides in this regular triangle or equilateral triangle, however you want to talk about it. So when we do the math here, 180 divided by 3 gives us a 60-degree angle. Okay, so that's step 1. We need this value. We need this value in order to come up with the rest of the story, right? We know we've got 360. Once we get these 2 known values under control, it's just a matter of doing 360 minus minus gives us what's left over. So step number 2, and let me just make sure we all saw what we were doing. So in this case, we're using the triangle. Triangle. Okay, the best I can do there. Now we're going to look at our nonagon and do the same thing. We're going to find the interior angle of a nonagon by using the sum of the interior angles divided by n. So the sum of our interior angles I'm putting inside here just because I'm losing space. We're going to do 180 times 9 minus 2 to give us the sum of our interior angles. When we do the math there, we're going to find that we have 1,260 degrees total inside our nonagon. We need to share that value with 9 of our friends. And so we're going to divide that value by 9 to come up with the value of each interior angle. When I do the math here, I get 140 degrees. All right. So again, make sure you pause the video if you need to, if I'm going too quickly. So we're left with x. We know that these 3 angles are tessellating. And what that really means is they have a common vertex, which essentially becomes the center of a circle. If I can draw a circle all the way around that common point of intersection, I know I've got a 360-degree tessellation going on. We know this guy's 60. We know this guy's 140. We're trying to come up with x. So in order to do that, we know we got 360 to start with. We need to do minus 60 for that triangle, minus 140 for our nonagon's interior angle, and that is going to give us the value of x. And when you do the math here, you will find you have 160 degrees, and that is what we were looking for. So tessellations look a little scary. A lot of times they do these sort of funky pictures, or rather, you know, this is some special pen, but in the end, we're just using all the stuff we've learned about angles of polygons. All right, at this point, I'd like for you to do the same kind of thing. Remember, we're looking for the value of BCD. In this case, we've got a regular hexagon. Here's our hexagon, here's our pentagon. The value of BCD is what the unknown is, so I'm going to put an X there. Okay, I am going to, because I've got a tessellation at work, I know I do because I have 3 angles that are converging to a center point, I'm going to draw a circle around that center. And I need to do the same exact thing I did above to determine the value of this angle here in this pentagon, the interior angle of a pentagon. And I need to find the interior angle of a hexagon. And then I need to apply the tessellation process. So pause the video, walk through these couple of steps, and check your work. All right, and so you should have gotten The fact that that angle value for BCD is worth 132 degrees.